Hello and welcome to another supplementary lecture for General Physics 2. This one covers the topics of light and sound waves and the Doppler effect. So we've talked in general about waves and the different types of waves. There can be transverse or longitudinal waves. And it turns out that the sound waves that are produced by me talking right now, by a speaker, by a musical instrument, are longitudinal in nature. So the diagram over here shows several different representations. First of all, recall that if you take a slinky, you can shake the slinky back and forth parallel to the direction that the slinky is stretched out, and you'll get these sections where you get compressed coils that travel down the length of the slinky to form the wave. Well, a similar effect happens in a column of air when you produce a sound wave. So here's like a cross section of a speaker. Inside a speaker, there's a cone that is vibrating back and forth. And as it does, when it pushes forward, it pushes air molecules closer together than they would be in their equilibrium position. Then when it moves backwards, air molecules actually get spread further apart than they would be normally. And so this sound wave of alternating high and low pressure regions travels forward, and here it's confined to inside some sort of tube. Similar to other wave patterns, we can identify the wavelength by just measuring the distance between the middle of one compression to the middle of another compression, or middle of one rarefaction region to the middle of another rarefaction region. If you were to put a series of pressure gauges along that tube, you would see that the pressure would be going alternatingly from low to high to low to high to low to high. And if you were to graph what air pressure would look like as a function of position, you would see going from low pressure to high pressure, low pressure to high pressure. High pressure situations would be where we have compressions. Some books call those condensations. And then rarefactions is where the air is spread out more than normal. And you could also characterize the wave amplitude by how high that high pressure or low pressure was relative to the equilibrium pressure. So if you make a louder sound, you're going to make regions of higher and lower pressure than you will if you make a quieter sound. The speed of sound at normal air pressure and normal temperature, standard temperature and pressure, is about 343 meters a second. Sometimes you'll look in a text and it'll say 340 or 330, but somewhere in that range. 343 meters a second is about 770 miles an hour. So although this is very fast and faster than you or I could run, it is not faster than, for example, the fastest moving object that we've made. And I believe it was in the 1950s was the first time that we made an airplane that was able to fly faster than the speed of sound. When you hear sound, the frequency determines the pitch of the sound that we hear. And if you've played a musical instrument, you're probably familiar with this concept. So when we hear a higher pitched sound, higher notes, soprano singer, those are higher frequency notes. Lower pitched sounds, low frequencies, basses produce low frequency sound. Humans detect sounds in the range of about 20 hertz, 20 cycles per second, up to 20,000 hertz or 20,000 cycles per second. So there's quite a wide range. You can, quote unquote, hear things that are oscillating at lower than 20 hertz, but you won't hear it as necessarily as a sound wave. So if something is vibrating back and forth only 2 times a second, for example, you may hear sound being produced by that, but you won't hear it as sound as you think of a sound being produced by some sort of musical instrument. 20,000 is, of course, the best ears, probably the youngest people, and most of us lose that high-end range of our hearing as we age and or as our hearing is damaged by various events. Ultrasonic refers to sounds that are above 20,000 hertz, and infrasonic is below 20,000 hertz. And again, these are just terms based on human perception. Ultrasound is routinely used for medical imaging purposes in the picture there on the top. Infrasound, lots of animals actually produce infrasonic sound that we as humans wouldn't hear as sound. Whales, elephants, this is some form of rhinoceros. all produce infrasonic sounds. All of them, however, produce sound at the same speed. And so even though frequencies vary and wavelengths vary of sound waves, the speed of sound remains the same. This is actually a good thing because if you think about going to some sort of musical concert, you sit wherever you sit in the performance hall, and you should hopefully hear all of the sounds played in the way that they were intended to be played, reaching your ear at the same time. If, for example, higher frequency sound traveled faster than lower frequency sound when you'd listen to an orchestra, you would hear the violins before the cellos, and the further away you got from the orchestra, the worse that effect would get. Now we're going to shift gears and talk a little bit about creating electromagnetic waves, light being one form of electromagnetic waves. So in this picture at the left, I have an alternating current source hooked to some conductor, and I'm not sure why in this text they colored that conductor the way they did, but this is how you create a simple antenna. So there's some conductor and there's an alternating current source. At time 0, that antenna is neutral. Well, a little while later, when the alternating current source has reached a maximum, it will have pushed positive charges to one end of that antenna and left negative charges at the other end of the antenna. Actually, more correctly, it will have pushed negative charges to the one end because the electrons are the things that move, and left the other end with the absence of electrons, but it's okay for this purpose to think of it as being positively and negatively charged. Well, if you have an object that's positively charged on one end and negatively charged on the other end, you get an electric field that points from the positive to the negative. A little while later, you are going to get the alternating current to return back to being that 0 point, at which time you have no electric field. A little bit later, you've pushed electrons to the top of that antenna. That's left the bottom of the antenna positive. Now the electric field is pointing up. A little while later, you're back to neutral, and this cycle repeats. Well, the alternating current generator is attached to this antenna. The current is switching direction periodically, and this electric field that's created propagates outward, and it turns out to propagate outward at the speed of light. This is how you make the electric portion of an electromagnetic wave. Now, we do so with a mechanical antenna, a piece of metal sticking up that we send an alternating current through. But you can also do it, in many other ways. In fact, atoms can produce electromagnetic waves by the movements of the electrical charges in the atoms themselves, or larger molecules, same kind of principle. The alternating current produces this electric field. Again, the electric field is continually changing in magnitude, and that becomes important for creating the other piece of the electromagnetic wave that we generate, namely magnetic field as well. So if I have a current that's going up and down in my antenna, at an instant in time when the current is going up, recall from our electromagnetism unit that you can predict the direction of the magnetic field. There's a magnetic field that circles around the antenna when the current is going up. And so you create a magnetic field that here to the right of the antenna is pointing into the page. Well, a little while later, that's going to have a current going down in it, and it's going to produce a magnetic field that's pointing out of the page. And in all of these situations, the magnetic field is perpendicular to the electric field, because remember, the electric field was parallel to the antenna. The magnetic field is perpendicular to the antenna, and so as you have charge oscillating up and down here in your antenna, you produce these regions of electric and magnetic field that are perpendicular to one another, and perpendicular to the direction the wave is ultimately traveling. So this effect is propagating outward from the antenna at the speed of light, and it consists of a whole series of oscillating electric and magnetic waves. I'm a kind of person that thinks a picture is worth 1,000 words here, and an animation is even better. So if you'd like, pause and go Google around for an electromagnetic wave animated GIF or some sort of illustration of that that's actually a little movie file, and you can see those waves oscillating in time, and that can be helpful to helping you visualize what in the world's going on. So let's think a little bit about electromagnetic waves. Would you characterize those as transverse or longitudinal? Well, recalling that they consist of both electric and magnetic fields, and both of those electric and magnetic fields are oscillating perpendicular to the direction that the wave is traveling, electromagnetic waves are considered transverse waves, and that actually bears out in some of the effects that we will look at in our optics studies, such as polarization of a wave. Electromagnetic waves, oddly enough, don't require a medium in which to propagate. Almost any other kind of wave that you can think of requires some medium to propagate in. So if you've had an earth science course, you've studied about earthquake waves. Well, they propagate through the ground. Sound waves propagate through commonly air, but they will also go through water, the ground, what have you, though the speed changes when they go through those different materials. Waves that you create in water require the medium of water to travel from point A to point B. So almost any kind of wave you can think of requires a medium, but it turns out electromagnetic waves don't. And this was something that troubled scientists for a long time. In fact, for a number of years, there was a theory of the universe that said the universe must be filled with a substance that had no mass and no discernible properties, but it was called luminiferous ether, because people thought, well, light travels through space, and space must have something in it that the light travels through, so they gave it the name luminiferous ether. However, like any good scientific theory, people that proposed the theory of luminiferous ether were able to predict, okay, when you have this ether, you should be able to see these effects. And it was a couple of scientists named Michelson and Morley who did an experiment actually trying to measure, I believe, the luminiferous ether itself, and ended up concluding that it must not exist because of their results. So if you like the history of science, you can read about the Michelson-Morley experiment on Wikipedia or many other places. All electromagnetic waves travel the same speed. So again, sound waves travel the same speed if you are in the same medium. And that's the same thing of electromagnetic waves as well. They travel the same speed as long as they're staying in the same medium. So it doesn't matter what kind of wave. We've divided electromagnetic waves into many, many different kinds. So visible light, that we'll talk about more in the end of this unit, isn't a type of electromagnetic wave, but radio waves, microwaves, X-rays, gamma rays, all of these things are different kinds of electromagnetic waves, and they have the same basic principle in the way they're generated. They just differ from each other in the frequencies and the wavelengths. And what was an odd finding, but led Einstein to propose his theory of relativity, is that electromagnetic waves travel the same speed regardless of the movement of the observer. And that is a bit of a tricky point. We're not going to get into it here, but if you find that kind of thing fascinating, the modern physics course that the physics department offers each spring starts with a few weeks delving into the theory of relativity and what that's all about. The electromagnetic spectrum is just, again, the collection of all of these different kinds of waves that are electromagnetic in nature. And so, again, they differ on their wavelength and their associated frequencies. So this graphic that I pulled off the internet has many of the major types here. Radio waves have the longest wavelengths. Their wavelengths are in the kilometer range, or can be as long as the kilometer range. But then as the wavelength gets shorter, you get into microwaves, which you're probably familiar with for using for cooking food in a microwave oven. A little bit shorter wavelength, you get into infrared waves. The visible spectrum is right here in the middle, and it has wavelengths that are in the order of hundreds of nanometers, and we'll talk more about that when we get into our optics work later. Above visible, at least in terms of energy and frequency, but shorter wavelength still, are ultraviolet waves that you may be familiar with. Those are the bad ones that give you the sunburn and things like that. Above that, even higher energy, higher frequency, and shorter wavelength are X-rays. used commonly for medical imaging. And then even higher energy rays are gamma rays, which are very short wavelength, very high frequency, and turns out also very high energy. And so, this little graphic gives a scale of how big things are. Radio waves are the scale of buildings. When we're talking about visible light, the wavelength of visible light is on the order of the size of protozoans. Ultraviolet, even smaller molecules. X-ray, the size of atoms. And when you're talking gamma rays, you're talking about things on the size of the order of atomic nuclei. Frequency goes the opposite to wavelength. So you start with low frequency and you go up to high frequency. High frequency also means high energy, and so gamma rays are the highest energy form of electromagnetic waves that we're aware of. And the temperature at which the radiation is most intense for emitting these wavelengths goes up as well. So higher energy corresponds to a higher temperature of emission as well. And this became important and also in the establishment of modern ideas about physics and the development of ideas of quantum mechanics, again, which is beyond the scope of this course. So we've said the speed of light is a constant, and it is a constant, again, as long as you don't change the medium. So various experiments have continuously revised our measurement of the speed of light in a vacuum. The current number that is used is about 299,792,458 meters a second. And change, I'm sure. And again, people devise new experiments to refine this measurement continually. For most of the things we're going to do in here, we're just going to use 3 times 10 to the 8th meters per second. That works fairly well for the detail of calculations that we hope to accomplish. And again, electromagnetic waves travel this speed in a vacuum, but they don't travel this speed in everything. Now, it turns out that air has a low enough density that we can use that speed of light in a vacuum when we're talking about the speed of light in air. But if light goes through, say, glass, it actually slows down. And that slowing down is important for what we observe in a piece of glass and understanding what we observe in a piece of glass, and that is that light that enters at some angle into that piece of glass will get bent as it travels through that glass, and that becomes important for designing, among other things, lenses. Again, more on that later in this unit. So we're going to talk a little bit about the concept of intensity. Intensity actually relates to all waves. All waves carry, and carries in quotes, transmit, I don't know what word you want to use there, energy from one point to another. And the amount of energy that they deliver per time is the power of that wave. We've seen power. You should have seen power back in Physics 1. Broadly speaking, it's energy per time. And so the power of the wave here is the energy that the wave is delivering per time. As waves spread out, though, the power spreads out, the energy spreads out, and passes through larger and larger quote-unquote surfaces. So if I have a speaker, when it gets to observer 1, that sound wave may only need to cover the area shown by diagram 1 here. But as I get out to observer 2, the waves are spreading out, and so now the wave is covering a larger area out here at 2. And as the area increases, the sound gets less and less intense. So we define intensity as the power that passes through a surface divided by the area of that surface. So intensity is power per area, and intensity has units of watts per square meter, since surface areas have units of units of square meters. Also, in any of these things, we approximate that none of the energy is lost. We're using an energy conservation idea here to say however much energy the speaker sent out is the amount of energy that passes through surface 1 is the amount of energy that passes through surface 2. That's not entirely realistic, of course, because if that sound wave runs into anything and causes that object to start vibrating, some portion of that sound wave's energy is going to be transferred to the object. But we don't have a model for that at this stage. Think about listening to sound, and now let's think about the intensity of sound waves in particular. If you listen to a sound that has a certain intensity, and a second sound that you hear is twice as loud, by how much has the intensity increased? Well, you would not be out of line with common answers if you say, well, twice as loud, that must mean twice the intensity. But it turns out if you actually measure it, intensity is power per area, that a sound that your human ear perceives as being twice as loud actually has 10 times the intensity, 10 times the power per area of a wave that you perceived to be whatever the reference level of loudness was. And humans therefore can hear sounds over quite a tremendous range of intensities. And so in order to represent those intensities, we find it mathematically convenient to use a logarithmic scale when comparing the intensity of one sound to another, rather than just a straight numerical scale, because the numbers, we just have to write a lot of numbers if we did not use some sort of logarithmic scale. So we define the intensity level of a wave using this relationship here. We take the intensity of whatever that wave is, and we divide it by a reference intensity. And that reference intensity is the number that is corresponding to the quietest sound that a human can hear. And I'm not sure how this number was arrived at. I'm not sure if all of us can hear a sound that intense, but essentially if you completely block out the sound out of any room and you produce a sound with a intensity of 10 to the minus 12 watts per square meter, a human ear can hear that. So that's the reference intensity. And then the intensity of whatever sound you're listening to goes in the numerator. You take the base 10 log of that, not the natural log of that. The base 10 log of that, multiply it by 10, and that is the intensity level, which we represent in units of decibels, even though a decibel is sort of just a placeholder unit. It doesn't transfer into any other sort of SI unit. It's just used to cue us in that we're talking about sound intensity. It's dimensionless, but we give it units just to keep track so we don't just have a number written down and not know what that number means. And one of the advantages of using this logarithmic scale is that if you have multiple sounds, the intensity of the multiple sounds is the sum of the individual intensities. So if you have a sound with an intensity level of 10 decibels and you put it together with another sound that has 10 decibels, the intensity of that together should be 20 decibels. All right, let's do a problem with this relationship involving warning sirens on the islands of Hawaii. If you've ever been to Hawaii, you may have seen some of these warning sirens around. I've been, but I haven't seen any of these go off, thankfully. They go off when there is an approaching tsunami, which could be a problem if you live on an island. Residents of Hawaii are warned of the approach of a tsunami by sirens mounted on top of towers. Suppose a siren produces a sound that has an intensity level of 120 decibels at a distance 2 meters away from that siren. Treating the siren as a point source of sound and ignoring reflections and absorption, find the intensity level heard by an observer that's 12 meters away, 21 meters away, and how far away can the siren be heard? Well, I find it helpful to sketch myself a little drawing. I'm not sure if this is useful, but I'm saying 2 meters away, we're measuring 120 decibels in terms of the intensity. So we want to know, how much do we get when we're 12 meters away? How much do we get when we're 21 meters away? First, we're going to find the power that is used by the speaker, or the power, I guess, transmitted by the speaker, using this intensity level equation. So the intensity level is 10 times the log of the ratio of the intensities. We want to solve for the intensity I. So the way I undo this is I'm going to move 10 to the other side of the equation. So beta over 10 is log of I over I0. Then the way you undo a base 10 log is you put it 10 to the power of that. So I'm doing 10 to the power on both sides. That gets rid of the log over on the right side, and now I have 10 to the power of beta over 10 equals the intensity over the reference intensity, which means the intensity anywhere is equal to the reference intensity times 10 to the power of beta over 10. Well, we know from the problem statement what the intensity is 2 meters away. So let's go ahead and use that. All right, our definition of intensity is power over area. Power is intensity times area, therefore. And the intensity, which we just found here, is the reference intensity times 10 to the power of beta over 10. The area, since we're treating this siren as a point source, would be the surface area of a sphere, because these sound waves would be assumed to travel outwards spherically in all directions from the siren. So the surface area of a sphere, you can look it up if you don't remember from high school geometry, is 4 pi r squared. And now we know enough stuff, because we know at a distance of 2 meters away what the intensity is recorded to be. So we can figure out what the power used by the siren is. So my reference intensity is 10 to the minus 12 watts per square meter. I have 10 to the power of, well, at 2 meters away, we're told it was 120 decibels. So I plug in 120 decibels for beta over 10 times 4 pi times 2 meters squared. And so note that I'll have a meter squared here and a meter squared here. They're going to go away and leave me with just units of watts. 10 to the minus 12 times 10 to the 12, well, that just washes out. That's just 1. And so I've got 4 pi times 4, that's 16 pi watts. And I'm just going to leave the pi in there because it's going to cancel out in a subsequent calculation. All right, so now we've set this up. We know how much power the siren is generating, and we can use that now to calculate, well, what's the intensity out here at 12 meters? What's the intensity out here at 21 meters? What's the intensity at any point? So the intensity level, again, beta is 10 log of the intensity over the reference intensity. But we know that the intensity is the power divided by the area. So we can replace the intensity in the equation with power over area. And then plug in what we know. So we know the power of the speaker is 16 pi watts. And then the area, when I'm out here at 12 meters away, is going to be the surface area of a 12 meter radius sphere, 4 pi times 12 meters squared. The reference intensity is still 10 to the minus 12 watts per square meter. And if you crank those numbers out, you'll find the intensity level is 104 decibels, which is still a pretty loud sound. But again, if you're only 12 meters away from the tsunami warning siren, you might want the intensity level to be pretty high. We do a similar calculation when we're 21 meters away. We just change the 12 in the calculation to 21 meters. And it turns out you're just under 100 decibels when you do that, which is still a fairly loud sound. In the textbook and in many places on the internet, you can find intensity level charts for common sounds. That's still pretty loud. How far away can we hear this thing from the siren? Well, again, there's some assumptions going on here that there's no reflections of the sound, there's no absorption of the sound by anything. But let's just get a rough number and see what that is. So the faintest sound that we can hear is that reference intensity, I naught. Now, got to be a pretty good day if your tsunami is coming and wherever this person is, there's no other objects producing sound so that she or he can hear this reference intensity, but we'll go with it. So we're going to say the reference intensity is the power over the area, which means the area would be the power over the reference intensity. The area, again, of a sphere is 4 pi r squared. We already know the power. We know the reference intensity, so we're going to solve this for radius. Radius is the square root of power over 4 pi times the reference intensity. We know the power of the speaker, that's 16 pi watts. We've got our 4 pi here. Again, it's convenient to leave pi's in because they keep canceling out. The reference intensity is 10 to the minus 12 watts per square meter. And so if you punch that all in, the radius you find is 2 times 10 to the 6 meters. That's 2 times 10 to the third kilometers, or 2,000 kilometers, which probably not very realistic, but you would hope your warning siren would reach at least tens of kilometers if you're going to be using it. However, again, here at 2,000 kilometers away, assuming none of the energy was lost, you would only hear this as the very faintest sound that humans can hear, which is probably not super useful. Probably a more useful calculation would be to say, how far away can the siren be heard at an intensity level of, 30 or 40 decibels, something in the range of normal sounds that we're used to listening to in everyday life. We're going to wrap up the conversation in this particular lecture by talking a little bit about the Doppler effect. Probably most of us have heard the words Doppler radar when we watch TV and we see weather forecasts. Doppler is used to track movements of clouds and movements of storm clouds during severe weather. What indeed is the Doppler effect? Well, the Doppler effect is the fact that if you have the object that's producing a wave or the object that is perceiving the wave moving, that there is going to be an observed change in frequency of that wave detected by the observer, because either, again, the source is moving, the observer is moving, or both are moving. And Doppler effect occurs in lots of types of waves. It's used in radar. If you've ever been on the receiving end of a speeding ticket and it says that you were measured by radar, the police officer used the Doppler effect to determine what speed you were going. The Doppler effect occurs in light as well, and so astronomers use this to figure out which galaxies are moving towards us and which galaxies are moving away from us. Again, it's a little bit different than what we're going to talk about in these slides when you're talking about the Doppler effect of light, because light travels the same speed regardless of the reference frame of the observer. And sound as well, and the specific example we're going to talk about in the next few slides would be a sound wave. Well, I have a little animation that's been playing on a loop over here, and what it is that little dot is the source of a sound or any kind of wave. If it were just stationary, then it would produce a series of concentric circles that would move outward from that spot. But because that source is moving, notice that in front of that source, the wave fronts sort of pile up, because as one wave front is moving away to the right, the object is also moving to the right before it generates the next wave front. And that causes a reduction in the wavelength of the wave in front of the moving source. If your wavelength gets shorter, your frequency gets higher because the speed of the wave remains constant in that medium. Similarly, behind the moving source here, because I generate a wavefront and then the object producing the waves moves away until it produces the next wavefront, the wavelength actually gets increased behind that moving source back there. The wavelength is longer and the frequency is smaller. And it turns out, surprise, we can characterize these with mathematical models. So let's reason through the physics here of what's going on with various situations where we produce the Doppler effect. So in my little picture up at front, I have a fire truck at rest. They flip the siren on, and there are two observers. They both hear the same frequency of sound because these sound waves move out from the fire truck as a series of concentric spheres, actually, three-dimensionally. And that means the two observers hear the sound with the same wavelength. Same wavelength means the same frequency because the speed of sound remains constant. But if that fire truck starts moving towards one observer, the wavelength toward the observer will get shorter, and the wavelength behind the fire truck to the other observer will get larger. And so the smaller wavelength will correspond to a higher observed frequency, and the larger wavelength will correspond to a lower observed frequency. Well, let's take the observer in front and first work out the situation there. The wavelength gets decreased. So the wavelength that the observer in front measures would be the speed of sound times the period of the wave minus the speed of the source times the period of the wave, because the source is moving towards that observer, and you can pull the speed of sound and the speed of the source out of that, and so say the difference between the speed of sound and the speed of the source times the period of the wave. Note that if the source happens to be going the speed of sound, which we're just using a v for here, this would all be zero, and so the wavelength would shrink to nothing, and that's where you get shock waves, and when you go faster than that, you get sonic booms produced by supersonic aircraft. The speed of sound is constant again if we keep the air the same that everything's moving in. So the speed of sound is a constant. That's just the wavelength observed by the observer times the frequency observed by the observer. Again, you can have any combination of wavelength and frequency. So if the wavelength has gotten smaller, the frequency has gotten bigger. Well, how much bigger has the frequency gotten? The frequency of the observer is the speed of sound divided by the wavelength of the observer. That's the speed of sound divided by the difference in the speeds, which I deduced up here in line 1, times the period of the wave. Well, the period of the wave is 1 over the frequency, so I can replace period t with f in the numerator, and I'm just actually going to pull it out of all of the terms here. And then I'm going to factor a v out of both the numerator and denominator of this fraction. So I pull a v out of the numerator, pull a v out of the denominator. That makes this leading term 1, and it makes the trailing term the speed of the source divided by the speed of sound. Of course, the v over v is just 1, and it goes away. And we're left with an equation that predicts the frequency that an observer would hear. Namely, it's 1 over 1 minus the speed of the source divided by the speed of sound times whatever the rest or the frequency would be when the source was at rest, or whatever frequency is being produced by that source. Away from the observer, very similar argument, but now the wavelength gets longer. So now you have the speed of sound times the period plus the speed of the source times the period. And that's the speed plus the speed of the source times the period. I go through a similar set of steps that I went through on the previous slide, and I find the exact same equation with the exception of this little plus here, because the frequency observed by the observer behind is going to get smaller. The source is moving, so this ratio here is going to be some positive number. 1 plus some positive number is greater than 1. 1 over that number that's greater than 1 is smaller than 1. So the observed frequency is smaller than the frequency that's being produced by the object that's moving. There's another way that you can observe the Doppler effect. If you have a stationary source of the sound waves, but you are moving relative to those sound waves, you will observe the Doppler effect as well, because you will encounter wave fronts more frequently than you would if you were just standing stationary. And so you will observe a higher frequency sound. Again, the speed of sound is constant, so that's the frequency times the wavelength. But the observed speed of sound seems higher because you are moving toward the sound. So the sound waves are going toward you with a speed of v, but you're going a speed v naught toward the sound source, and that makes the sound appear as though it were traveling at a higher speed. Just like if you are standing by the highway and watching cars go 60 miles an hour at you, they appear to go 60 miles an hour. If you start running at 10 miles an hour into traffic, not recommended by the way, and have the wherewithal to think about it, the cars would actually appear to be moving 70 miles an hour towards you in your frame of reference. So for this observer, the observed speed seems higher. It's the speed of sound plus the speed of the observer. The observed frequency also seems higher because you're running into wave fronts more rapidly than you were before. So the frequency that the observer would encounter would be this apparent speed of sound, which we're calling v prime, over the wavelength, because nothing is changing about the wavelength. The distance between the wave fronts is still the same because the source is stationary. Well, this apparent speed of sound is, again, the speed of sound, the actual speed of sound, plus the speed of the observer, divided by the wavelength of the sound. Wavelength, of course, is speed over frequency, so I can replace wavelength with speed over frequency. I can pull frequency out to the edge here because I have numerator over denominator, and so again that whole multiply by the reciprocal when you have a fraction in the denominator rule comes into effect. So then I have speed plus speed of the observer over speed times the frequency, and again commonly we'll factor speed v out of all of this, and we're left with the observed frequency is 1 plus the speed of the observer over the speed of sound times the frequency that is being produced. And so if you are walking toward the sound waves with some speed, this fraction here is going to be some positive number. 1 plus some positive number is going to make an observed frequency that's higher than the frequency that's emitted by the source. Similar logic if you are walking away from the source. Sorry, my picture didn't change. The book that I grabbed these out of only had the one picture. But the observed speed seems lower now because you're walking away, so the sound wavefronts don't hit you as rapidly as they did before. That makes the frequency seem lower as well. All of the algebra here is the same except for the minus sign, and we end up with an observed frequency that is 1 minus the speed of the observer over the speed times the frequency that's generated by that stationary source. If you are the kind of person that likes efficiency, some books will give you this general Doppler equation, and that has everything in it that you could want. It's got the possibility of the moving observer, and that shows up in the numerator here, and it has the possibility of the moving source, which shows up in the denominator here. And so this will solve any particular problem that you want. You just have to remember when to use a positive or when to use a negative. And again, you have to think, okay, if the observer is moving towards the sound, the frequency will get higher, so that's going to be the plus. If the observer is moving away from the sound, the frequency is going to get lower, that's going to be the minus. If the source is moving toward the observer, the frequency gets higher, and that's going to be a minus because we got this term in the denominator here. If the source is moving away from the observer, the frequency gets longer. I need this denominator rather to be greater than 1, so I'm going to choose the plus option there. All right, let's conclude then by solving a sample Doppler problem. Jim is speeding toward James Island, I don't know if it's named after him, with a speed of 24 meters a second when he sees Betsy standing on shore at the base of a cliff. Jim sounds his 330 hertz horn. What frequency does Betsy hear? And then Jim can hear the echo of his horn reflected back to him by the cliff. So the sound waves are going to go here, be heard by Betsy, but they're also going to bounce off the cliff and come back to Jim. So is he going to hear a frequency greater than, equal to, or less than the frequency heard by Betsy? And we're actually going to be asked to calculate that in part C. All right, so I just went ahead and used that big equation using a prime for the frequency of the observer. So in this case, I have a moving source and the observer is at rest. So this whole term in the observer in the numerator is just going to be 0. So I'll have 1 over 1, and then I have to decide, okay, the source is moving toward the observer. That will make the observed frequency higher, which means I have to choose the minus sign for the denominator. And then it's just a plug and chug. I have 1 over 1 minus. The boat's moving at 24 meters a second. Sound is assumed to be moving 343 meters a second. The frequency that's produced by the horn on board is 330 hertz, and if you crank that out, Betsy will hear a frequency of 355 hertz. What about Jim? What's he going to hear? Well, those 355 hertz waves are going to bounce off the cliff, and they're going to come back to Jim. And now you have a situation where he is a moving observer moving into that sound. So he's going to encounter wave fronts at a greater rate than he would if the boat were stationary. And so he is going to hear an even greater frequency than Betsy does. The cliff reflects these 355 hertz waves, but now Jim is a moving observer moving at 24 meters a second towards those 355 hertz sound waves. So again, we can use that same master equation. The frequency that Jim would observe would be 1 plus, and here is the moving observer. He's moving, and I choose the plus because it's a higher frequency. He's moving at 24 meters a second. The sound is moving at 343. But the source of the waves is also moving, and that's the denominator here. And then I'm using the 330 hertz out here. Another way to do this is use the 355 hertz out here and assume the cliff is the producer of the wave, and then just make the numerator 1 in here and negate the movement of the source of the wave since the cliff itself is stationary. Either way you do that, you get the same answer and you get 380 hertz for the calculation. So this concludes the supplementary lecture for General Physics 2 for light, sound, and Doppler. Again, it's hoped that if you are watching and listening to these, they are useful resources for your learning. And as always, if you've noticed a mistake in the presentation, the instructor would very much appreciate hearing about it. Thank you.